Okay, everybody. So this is the lecture for week 10. And what we're going to be doing is looking over the zyBooks Chapter 5. So the zyBooks Chapter 5 is due soon. It's actually due in a week. The reason for that is it's a very short assignment and it only has challenge activities in one section. So we'll kind of go through this. So if you look at section 5.1, this is the wrong date, by the way, so don't pay attention to that. So what this chapter does is it goes over just a few sections, and there's not very many exercises because a lot of the work is in the next chapter after this one. So we'll go through it and look at it. So, they're going to say, hey, do we represent things with bits? Yeah. Um, do we represent instructions with bits? Yeah. Okay. Congratulations, you finished section one. And then we get to 5.2, which is on addition and subtraction, which we've already covered. So um, we know that when you add bits, you just need to remember how to carry. So like in this example here, when we're adding these two, what are they? 32-bit numbers? I don't know. I didn't count. However many bits they are. What you do is you just add like normal, right? So you just do it in binary. So like 1 plus 0 is 1. And then you have 1 plus 1 is 2. But when you have 1 plus 1 is 2, you write the 2 as 1, 0, right, in binary. So you put the 0 here and you carry the 1. Then you have 1 plus 1, which is 3, but 3 is 1, 1, 1. So you put 1 here, you carry the 1, and then we have 1 plus 0, which is 1. And then the rest of these just are going to be zeros till the end. And looking at the answer at the end, we see that they were adding 7 and 6, and we got 13 as a result. So we already covered that in class in person. So that should be nothing new. The other thing we learned how to do was to write things in two's complement. So, like for example, the way you would write -6 in two's complement is written right here. Uh, and the whole point of two's complement was that if you have a number written, a positive number or a negative number in two's complement, you can add them and get the correct result with the same exact algorithm for addition or subtraction that we were already using. So you could add negative numbers with the same rule as far as how to carry numbers and stuff. And so that's kind of the big deal, right? So here in this example, they have 7 plus -6, and they get a 1 here, which is the correct answer, right? So the normal rules follow, um, but just I'll go through this briefly just to explain something because the carries do something weird here. So I'm not going to cover how to convert things to two's complement, but assuming we have the 6 as -6 in two's complement, then we can add them. So let's see. If you do 1 plus 0, you get 1. If you do 1 plus 1, you get 2, 1, 0. So you put the 0 here and you put the 1 up here. But then you have 1, oops. Then you have 1 plus 1, which is 0. Sorry, it screwed me up when the page moved, so I don't know where I'm looking at. So I'm going to start over. 1 plus 0 is 1. 1 plus 1 is 2, 1, 0. So you put a 0 there. You carry a 1 right here. 1 and 1 is 2. So you put a 0, carry the 1. 1 plus 1 is 2, 0, carry the 1. And you continue this process. 1 plus 1 is 0, carry the 1, all the way to the end. And when you get to the last bit, you're going to go like 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. But we're out of bits, right? So when we carry the 1 here, there's nothing to add it to because we have a precise, uh, a finite number of bits for our calculation. So a 1 ends up over here with nothing to add it to, and it just disappears. So that's what happens when you have two's complement numbers is you expect that kind of carry thing to carry all the way to the past the number of bits that you actually have. Um, so there you go. You can do these exercises. They're just participation activities. So, if you do 1 plus 0, 1 plus 0 is 1. So W is 1. And then you have, well, the carry bit, we didn't have to carry anything. So if we didn't carry anything, then up here where you would carry, you can just put a 0 if we didn't carry anything. So 0 and 1 is 2, which is 1 to 0. So you put a 0 where the x is, and you carry a 1 to where the b is. 1 plus 0 is 1. So y would be 1. So I think they're asking for the whole answer here. So if you added these all up, what did we end up with? Well, the all zeros and then yxw. Y is 1, x is 0, w is 1. So 1, 0, 1. So it must be this one. Okay. So subtraction, remember, so they are going to make you write this number. Like this is a negative, looks like 4. So if you wanted to figure out what negative 4 was, first of all, to know what we were putting here, this is where you'd have to remember how to do um, 2's complement. So I'll come over here. So 4 is 100, right? In base 2. But if we write it with more bits, right? Let's go like this. Put some more bits in there. Then just because there's zeros off this side, then our steps for converting to find out what negative 4 would be is, remember, we have to, step 1, invert all bits. So we would have, instead of this, right, we would end up with 1, 1, 1, 1, 0, oh, 1, 0, 1, 1. And then after you do that, step 2 is we have to add 1. So add 1, we'll see what we get. So you get 1 plus 1. Oh, right, this is annoying to do. Is 0, carry the 1. Then you have 1 plus 1 is 2, which is, dang it, stop that. 0, carry the 1. I put these dots here just to stop this from doing that to me. 1 plus 0 plus 0 is 1. 1 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 plus 0 is 1. So you end up with this. Um, so if we kind of just think of this as, I don't know what that is, go away. If we just think of there being, we could have added more zeros at the beginning of this, right? Well, that would just end up with more ones down this way. So this is just what negative 4 is. So minus 4 is 1, 1, 1, 1, 1, 1, 0, 0. So the DCBA is 1, 1, 0, 0, right? That's what we had here. Okay. Then if we have to add these, right, we're basically adding this. We had a bunch of zeros, and then we had, but a bunch of zeros, and then 0, 1, 0, 1. And then we have what we just came up with, which was that. Wait, no, it was this. Sorry. And we would just add those, right? So add. Life is hard. And oh, why? No, you let me. I, oh, I hate you so much. It won't let me move over to the left here. Okay. And now we can add using regular binary addition here. So we have 1 plus 0 is 1. Here's 0 plus 0 is 0. 1 plus 1 is 2. So that's 0, carry the 1. 1 plus 1 is 2. So 1 plus 1 is 2. So that is 0, carry the 1. 1 plus 1 is 2. So that is 0, carry the 1. 1 plus 1 is 2, which is 0, carry the 1. 1 plus 1 is 2, and so on. And then 1 plus 1 is 0, carry the 1, but we're out of bits. So we just end up with 1 here. So what is the ZYXW? It is 1. All right. And it said if a 33rd sum bit existed, what would the value get? Well, like we only did this with 4 extra bits here, but like they write it with a dot dot dot. So um, if you could have an extra bit, what would it be? Well, it'd be the same as the ones that were next to it. What? Oh, yeah, the one that I don't like the way that this is worded here. So what happens, right, is your last computation is always like 1 plus 1, which is 2. So it's 0 and then like carry a 1, right? And they said, well, what would that bit be? And they say 1 because if you brought that down, it would be a 1 there. But if you were carrying it out to one more bit, then actually these zeros would have been extended and these ones would have been extended an extra bit. And we'd still end up with the 0 there, not a 1. But they meant for it to be 1, so 1 it is. But I don't really like that. And then now we have a challenge activity. And so this challenge activity is I think the only one we have to do, or the only section we have to do them in. So they're going to make us add some numbers, but this should not be so hard. So we'll just go through, right? So I think we click on these and it toggles them. So you just add. So 0 plus 0 is 0. Then this would be carry is 0. We don't need to carry. 0 plus 0 plus 1 is 1. Don't need to carry. 0 plus 1 plus 0 is 1. Don't need to carry. 0 plus 0 plus 0 is 0. Don't need to carry. 0 plus 0 plus 0 is 0. Right? So we're just going through and making sure that we can do these additions. Um, so maybe there'll be some carries here. 1 plus 0, 1. Don't carry. 0 plus 0 plus 1 is 1. Don't carry. 0 plus 1 is 2, which we write as 1, 0. So that's 0, carry a 1. And now 1 plus 1 plus 1 is 3, 1, 1. So it's 1, carry the 1. 1 plus 0 is 1. And we're done. Okay, let's just skip ahead to number 4. They're adding negative numbers now, but remember, there's nothing different about them. So just this -8 is written in 2's complement, but we add like normal. So 1 plus 0 is 1, carry nothing. 0, 0, 0 is 0, carry nothing. 0, 1, 0, that adds up to 1, carry nothing. 0 plus 0 plus 1 is 1, carry nothing. 0 plus 0 plus 1 is 1, right? And then they tell us that that's -3. So same thing. 0 plus 0 is 0. 0 plus 1 plus 0 is 1. 0 plus 0 plus 1 is 1. 1 plus 1 is 2. 1, 0. So 0, carry the 1. 1 plus 1 is 1. And you'd carry the 1 and it'd be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And it would just continue to the end. So there we go. So that's just adding. Hopefully not so bad. Now they do talk about overflow. And so overflow is going to be when you try to add numbers that are too big and they overflow. And so they'll give you kind of a rule here. So The lack of a 33rd bit means that when overflow occurs, the sign bit is set with the value of the result instead of the proper sign. Yeah, so when you add, like the last bit is meant to be the sign bit, right? So 0 on a positive number and 1 if you had a negative number, which we don't here. And they're showing you an example of like this is a positive number, right? You can tell that this is a positive number, the top number, because it starts with the 0. And you can tell that the bottom number is a positive number because it starts with the 0. And so when you add a positive number and a positive number, of course, you should end up with a positive number. But when you add these two positive numbers, you get the bottom number here, which you'll see ends up with a 1 here. So this number looks like a negative number, right? Because we know that the first bit is the sign bit, and when it's 1, we have a negative number. And so we added a positive number and somehow got a negative number. And so that's overflow. Um, so you'll be able to tell that that happened because you'll get the wrong answer, right? Like this is a like probably a pretty silly chart here, but what they're saying is if you're adding a positive and a positive and you get a negative, that's bad, right? So that's overflow. But if you add a negative and a negative, you should get a negative. So if you end up with a positive, that means there was overflow. Um, if you do an A minus B and you have a positive number minus a negative, your result should be positive. So if it's negative, something wrong happened. And if you had a negative number and you subtract a positive number, you should end up with a negative number. So if it's positive, that means something happened, overflow, right? So they're basically just saying if you add two numbers and the sign comes up wrong, that means there was overflow. That's all that's saying. So it's kind of a long chart just to say that. So if you were looking at this right here, without looking at the whole numbers, you should be able to look at the top one and say, well, it was positive and positive. But then the first bit is 1, indicating a negative number, so there must have been overflow, right? On this one, if you have a negative and we ended up with a negative, that's correct, right? So no overflow. Here we have a positive number and a negative number, and we ended up with a negative number. Um, right? So they actually didn't cover that case where we have a positive plus a negative, right? If you look at the chart, um, they did positive, positive, negative, negative, and this looks like positive, negative, but this was when they were subtracting, which this is addition. But when you add a positive and a negative number, you could get a positive or you could get a negative. So you can't really say for sure which way this was. So probably no overflow, right? Um, oh, I said probably, but we should have thought about it better. Um, you can't overflow when you add a positive and a negative because you always end up like if you think about it, if you add a number like, let's say positive 500 and you add it to like negative 200, right? You don't have to worry about how big the result is, right? Because, when you do like 500 minus 200, you always end up with a number whose magnitude is between 500 and 200, right? Um, you can't end up with something bigger than 500, and you can't end up with something smaller than negative 200 because the signs are opposite. So they'll cancel each other out partially. So you can't possibly overflow in that case. Um, okay. So you can read the rest of this. They're going to start talking about the arithmetic logic unit. That's a normal thing to talk about in a computer hardware class. And that's just the thing in the CPU that does the calculations. So ALU, arithmetic logic unit, it's what does the addition and subtraction. and sometimes other things. Now we're going to be doing MIPS, assembly language programming, later this semester, and we'll start seeing what instructions the CPU supports. And those instructions are going to be things like add immediate, subtract, add immediate unsigned, um, and so on. Now, you don't have to pay too much attention to those, but they're going to start referring to them in some of these sections just because. Okay. So, I mean, we can do these just like the MIPS add I, that's add immediate, and sub instructions may result in an exception. You can read up here to see that that's true. Um, these do not. You can read up here to see that that's true. These can result in an overflow. I mean, any of them can result in an overflow, but I don't know um, what they meant there. The MIPS instructions only operate on unsigned operands. Yeah, so the U means unsigned, but you can still use the instructions even if your data is negative. So that's weird, but that's the point they're trying to make there, that the instructions are badly named. Um, that's false. A compiler for the C language never generates these. I believe that's true. Um, okay. So again, you can kind of read these last things. This is what MIPS assembly language looks like. Again, they cover this later. You can't really understand it now, but this is just an example of what assembly language looks like, where we're adding two numbers. We're doing an exclusive OR operation. This is a comparison, um, checking if one thing is less than another thing. Um, this is a branch. That's how you do if statements, right? If you jump to one place in the code or jump to another place in the code, you use a branch instruction, and so on. But we don't really need to think about that too hard. Now let's get to the next section here, 5.3 multiplication. So we've done this on the board, I believe, at least in either on the board or in the previous um, set of video. But you multiply using the exact same rules that you used for multiplying when you multiply um, numbers by hand that are in base 10. So binary multiplication is not any different. So I think we've done this, but we'll see it on the board later. So I'm not going to do this, but it's exactly the same as normal multiplication. Actually, I guess we are doing it because we'll do this exercise here. So when you're multiplying this number, which looks like 1, 2, 4, 8, so the 8 and 4, so it's like 13. Oh, it says it up here, 13. And we're multiplying by 6. So when you're doing this, right, normally what you do is you take the entire top number and you multiply it by this first digit. Now, when you take the entire top number and you multiply it by 0, of course, you're just going to get all zeros here, right? And then when you move down to the next row, you put a blank space. And then this right here is going to be the entire top number multiplied by the second digit. So we're going to multiply 1101 by 1. And the thing about that is when you do 1101 times 1, it's just going to be 1101, right? And when you do the third one, it's going to be the entire top row times this third digit, which is also 1. So 1101 times 1 is 1101. And so you start to notice that for all of these things that they're calling the partial products, the only possibilities are 0000 if we were multiplying by a 0, and 1101 if we were multiplying by a 1. So when you get to the fourth one, it'll be 1101 times 0, which is just going to be 0, all zeros, right? And then to get the answer, you have to just add these rows, which, uh, okay. That's kind of awkward. Oh, if we were going to do this, I'll copy this. And what were they? So the first one was 0, 0, 0, 0. And then the next one is going to be 1, 1, 0, 1. And 1, 1, 0, 1. And then the last one was 0, 0, 0, 0. And then we have to add those numbers up using normal addition rules. So down here, you go bring the 0 down, you get 0. Bring the 1 down, you get 1. 0, 0, 1 is 1. 0, 1, 0, 0 is 1. 1, 1, 0, that's 2. So that's a 0. Carry a 1. 1 plus 1 is 2. 0, carry a 1. And then 1 plus 0 is 1. So this is what we get here. Right? The largest product resulting from multiplying of a 7-bit multiplicand and a 7-bit multiplicand is when you multiply two numbers together, it could double the amount of bits. So a 7-bit number times a 7-bit number could be 14 bits long. All right. Now, this hardware right here is trying to illustrate the process that we just used here. So the important thing to keep in mind about this, let me just kind of delete these carry bits, is that these numbers either are 0 or they're 1101, which was the top number that we were multiplying, right? And then what we had to do was we either added 0 or we added 1101, but then some of the 1101s are like shifted over, right? So like this one is shifted over by 1 bit. This one is shifted over by 2 bits, right? This one's shifted over by 3 bits, although it's 0000. So we don't care so much. And so this hardware is the hardware that does it. So what hardware do you need to actually do this? Well, we need something to shift left. Why shift left? Well, this 1101, it's all the way on the right side. It could have been here. 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 So we could have had a 1101, 1101, 1101, 1101. So that's the multiplicand, but it's been shifted left by either 1 bit or 2 bits or 3 bits. So we need a way to shift the multiplicand by 1 or by 1 bit to the left. That's a piece of hardware you need. Now, the multiplier, it says we need to shift right. So why? Well, because the first time we go through this, we take this top thing, we multiply it by 0, right? But then the next time, we don't want to multiply it by 0, we want to multiply it by the 1, right? So the easiest way to do that is to move this entire thing to the right. And so like if you have 0, 1, 1, 0 to start with, right? We look at this bit 0 all the way on the right, we're going to use that. But then the next time we do part of the multiplication, we want to look at the 1. So the way you look at the 1 is you move everything to the right by 1 spot. Like that. Now you can fill in this, you can fill in an extra 0 there if you want. So that's like move to the right. And then the next time, we'll move it right again. And we'll look at that one. And the next time we'll move it right again and we'll look at this one. So the 0, 1, 0, 0, the things you see in the right digit, that's what this was a 0 because this was a 0. This was 1101 because this was a 1. This was 1101 because this was a 1. And this one was 0000 because this was a 0. Right? So the thing that is going to do that is a right shift on the multiplier. Okay. And then the control test is, are we adding 0 or are we adding 1101? So this is basically going to form a loop where we're going to shift the multiplicand over to the left by 1 bit, 2 bit, 3 bits, 4 bits, etc. We're going to shift the multiplier to the right 1 bit, or 1 bit, 2 bits, 3 bits, 4 bits to the right. I said actually 1 bit, 2 bit, 3 bits. Um, Shift the multiplier to the bits to the right. Then, based on the rightmost digit, we will decide whether we should be adding a 0000 or whether we should be adding a 1101, right? Because sometimes it's 000, sometimes it's 1101. Uh, so that's based on looking at one particular bit. Then when we're done, uh, these things all need to be added together. And when we're done, that is the product. So essentially, this thing does what we did by hand. Now you can read the instructions here, right? So it says control checks multiplier 0. That's the rightmost bit, right? So these bits are going to be the multiplier 0 to determine when to shift the multiplicand and multiplier registers and when to write new values. Okay. If multiplier 0 is 0, multiplicand is shifted left 1 bit. Multiplier is shift right 1 bit. If multiplier 0 is 1, multiplicand and product registers are added. So only if it's a 1 do we add them. The multiplicand register is again shifted left 1 bit and the multiplier is shifted right 1 bit. The process continues 32 times if you have a 32-bit number. So this would take 32 clock cycles, possibly, to do this multiplication for a 32-bit number times a 32-bit number. All right. So here's the logic actually written out into the flowchart. Start, look at the first bit. If it's 0, we don't add anything, right? Because if this digit is 0, that means we should be adding 0. But you don't need to actually add 0. So we do nothing here. And then we shift the multiplicand register left, shift the multiplier register right, then check if we're done. If we're not, we go back up here. Then you look at the next bit. So we'd be looking at this bit, the 1. If it's 1, we go this way. This time you have to add the multiplicand to the product. So that's why you'd be adding the 1101. Then you shift the multiplicand, shift the multiplier right, check if we're done. No, come back up here, look at the next bit. So we'd be looking at this bit. It's a 1, so we add the multiplicand to the product, shift left, shift right. Done. No, back up to the top. Then we'd be looking at the last bit, 0. Don't do anything, shift, shift. Are we done? Yes. So essentially, this right here is deciding whether we're adding 0 or whether we're adding 1101. And we're not adding just, 1101 or 0000. We're adding 1101 or shifted to the left by some amount. And that's what these shifts are doing. All right, that's it. So, there's no challenge exercises on these, but you can go through and try to understand them. So, like each step of the multiplication algorithm shifts the multiplier register 1 bit to multiplier right, right? Just keyword multiplier and multiplicand. The multiplier register is how many bits wide? Well, look, we look up the chart. Multiplier 32 bits. Each step of the multiplication shifts the multiplicand 1 bit or to the what direction? Well, that one goes left. Multiplicand left. Multiplicand register is 64 bits. It has to be twice as wide. That's because, remember, if you multiply a 32-bit number by a 32-bit number, you could end up with twice as many bits, 64. The product register, well, we could take 64 bits. So 64. Each iteration of the multiplication algorithm consists of blank basic steps. How are they counting? I guess one, two, three. They got these numbered. Is it three because that's what they numbered, or is it one, two, three, four, five? I don't know. Um, three maybe because that's what they numbered. All right. Um, it's just a modified version of the hardware. So we want to take one clock cycle per step. Um, so the idea is that like while we're doing step two, we could be doing the next step one, right? So you could have something doing step one, something doing step two, and something doing step three all at the same time. And in that way, uh, 32 bits would take 32 clock cycles, as opposed to what if this was one clock cycle and this was one clock cycle and this was one clock cycle, then it would be three times as long to run. So we can do those in parallel, they say, and go faster. Also, all modern hardware does this in the entire thing in one clock cycle. So that's interesting. All right. So refined multiplication hardware halves the width of the multiplicand register. Does it? Yes, 32. The multiplier register is removed and placed inside of where's the multiplier? It, I don't see it here. It must be inside the product register. The ALU adds the 64-bit product and the 32-bit multiplicand and then stores the result in the product register, I guess. Oh, I didn't read. Stored in the product register. Wait. Oh, it adds 32 bits to 32 bits, not 64 bits to 32 bits. All right. So let's see here. The prison called. So they want us to kind of trace through this and see if we can. So let's try to do this. So this is a chart showing like this entire process written out. And so we'll follow it from the beginning, but obviously only certain things here we have to fill in. So we're multiplying 5 times 12. Okay. So they have this is 12 and this is 5 is the order that they put them in. Okay. So to start with, they take this 5 and they gave it extra bits, twice as many bits. So they just put zeros at the beginning. But this is still 5. This is 12 that doesn't need extra bits, so they just left it. And the product is where our answer is going, but right now it starts out all zeros. So that's where you start. To multiply 5 times 12, you just put the 12 here and the 5 here. Okay. Then what we have to do is go through the steps. So um, the step says start step one. So these are the 1, 2, 3 are 1, 2, 3 here. So um, test multiplier 0. So you're looking at the bit uh, all the way on the right-hand side. So this 0, and it's a 0, right? So because that's a 0, we go this way. Multiplier 0 equals 0. So we don't have to do 1a, right? So if this says no operation, the other possibility would be like to actually do something for step 1a. So because this bit is 0, we do nothing. Then we need to do step 2 and step 3. So if we did nothing, we should shift the multiplicand bit one left. So to fill out this, to get from the top row to the second row, the multiplicand should shift one step. So we're on step 2 now, actually. So from here to here, we move 1 bit to the left. That's what step 2 does. So 101 all the way on the right. Now it's 101 with an extra 0. So this moved left. That's step 2. We did nothing to the product step. Then for step three is supposed to shift the multiplier 1 bit right. So uh, this should 1100, we're moving to the right here. So it goes 0110. So the 1's move to the right. And that's it for that entire thing. Then now we want to go down to the next big step. So we're at the 32 repetition. No, so you go back up top. And now we're looking at this row where we left off. And we are now going to look at the bit 0 of multiplier again. So we're looking right here, this bit. So this is a 0. So just like last time, we are 1A is going to be nothing, right? We're not doing a 1A. So there's like no 1A over here. So that's this. Oops, wrong place there. Um, and then we write it all out. And then we need to do step 2. Step 2 is to shift the multiplicand 1 bit left. So here's the multiplicand. It needs to go 1 bit to the left. So we're going to add another 0 at the beginning, take 1 off the beginning. So the 101 moves over to the left. So if we took this and everything moved 1 to the left, it would be, I think, this one, right? Is that what we'd get if this moved to the left? Did I put that in the wrong place? What? It's not letting me. Okay. So we do that, and that finishes out step 2. Step 3 is the right shift. So if you take this right here, and everything needs to go right. So instead of 0110, it'd be this one. If we move everything to the right by 1 bit. And then we move on. They really should fill these in with the like the number that we put for B should be in B and here. So it's a little bit annoying. Um, now imagine what C is. So C is this, right? 0011. So this is 0011. And so when we get to the next back up to the top and we're checking multiplier 0 this time, we'll be looking at 0011. So the right bit is a 1 actually. So when we're doing this first step A, we'll be looking at 0011. So we will actually head this way. And so we need to add the multiplicand to the product. So we do that. And by the process of elimination, this is um, we need to add the product equals the product plus the multiplicand. So you would have to add this number and this number together because this is multiplicand and this is product to get what goes into E. But there's only one possibility, so it's just got to be this. Okay, and that was tracing through the multiplication process. So it's not that bad. Okay. Um, you can click through these. These are specifically asking about MIPS, which we're going to see later. You don't need to know it now. Um, all right. So we need to stop here, but I will continue this lecture in the next video.